Hi guys, welcome to another Tuesday Tune. This week I figured I would talk about some of the compromises involved in suspension and how they arise. The big one I wanted to cover comes down to different resonance modes. These are probably not terms that most people are familiar with. Resonance, for those who are not familiar, it's basically things are oscillating out of control. So that tends to happen if you imagine holding something on a spring, a weight on a spring, bouncing it up and down. You can pick just the right frequency, the thing will basically bounce out of control. That is essentially what resonance is in the simplest sense. Resonance modes refers to different manners in which this state can occur. That typically means different frequencies and different directions. Within suspension, we're going to look at that in a single direction, just vertical. We're going to have to make a huge number of simplifications and basically assumptions in order to try and cover this in such a way that it means anything to anybody. But basically what I am going to try to explain, is why it is that we seem to have this back and forth between things being considered underdamped and undersupported and overdamped and harsh. The reason is primarily a mathematical one. There are pragmatic factors that are involved, but it is primarily a mathematical thing. So let's get stuck in. What I've got drawn up on the board here, some of you guys will have seen diagrams like this. It's basically a diagram of a 2 degree of freedom mass spring damper system that's commonly used to represent a single wheel of a vehicle, often referred to as a quarter car model. This is our ground. This is the tire and the stiffness of it. So K represents the spring rate. We have an unsprung mass here that the tire pushes on, which would be our hub and our wheel. K spring would be our spring rate of the actual fork or shock as measured at the wheel, right? So this is only an effective thing, not necessarily a real spring rate that's happening directly at your shock, for example, or at your fork for that matter. C of the damper, that is our damping coefficient as measured at the damper. Now, even this is very simplified. It assumes that we only have one number for this, one number for that. In practice, that's rarely the case. The unsprung mass here is our wheel and either fork lowers or rear axle and swing arm and whatnot. This is an effective mass for the most part. It's usually not, strictly speaking, an actual mass that you can easily measure because there's all sorts of other polar moments of inertia and whatnot that affect that effective mass. It's essentially a measurement of inertia required to be moved out of the way. Sprung mass is the same deal. Sprung mass typically refers to the rider and the front triangle of the bike, and everything that's rigidly attached to it: cranks, seat post, handlebars, so forth. All those things are part of your sprung mass. Before we go too far down the 2 degree of freedom rabbit hole, quick primer on one of the main things that matters here. So transmissibility of vibration basically refers to what the input is. So for example, running over a speed bump, and how much movement of the sprung mass there is. So if we were only looking at this top half of this, for example, and ignoring the damper, so really just a single degree of freedom mass spring system, what we see is something where if you go over it slowly enough at a frequency input that is much lower than our natural frequency, so basically zero frequency, you drive very slowly over a speed bump, the car will lift up almost exactly as high as the bump itself. If you manage to hit it at just the right speed, you'll have something where, in theory, this goes kind of to infinity at the natural frequency. And once you start hitting frequencies that are much higher than that natural frequency, that's supposed to line up with that, then the transmissibility drops. And that means that if you run over a curb at very high speed, or let's say you run over like a 100 diameter pipe, right, that's bolted to the ground on your bike. You run over that at 40 k's an hour. 100 diameter will obviously displace the wheel up a long way, but it won't move the rider anywhere near that far. And that is basically saying that once we've created an input that's faster, basically at a higher frequency than the natural frequency of the system, the transmissibility actually drops. So that means that for 100 of displacement at the ground, we're seeing significantly less than that at the rider. That's the whole job of suspension. So in an ideal world, we kind of want everything, all our bump inputs anyway, to be at a higher frequency than our natural frequency for maximum bump absorption. What does that mean? That means we want to make the natural frequency as low as possible. So natural frequency is often referred to as square root of k on m. So this is k, that's m. So if we want to make this value, which is the same as fn, as low as possible, then what do we want to do? We want to make that number as high as possible or that number as low as possible. That basically means relative to our weight, the softest spring rate is going to move that down as far as possible. Now, we've covered this plenty of times in the past. There's obviously limitations on how soft your spring rate can go, so we hit a practical limit there. Your spring needs to actually hold you up, for starters. It's no good if your body weight bottoms your spring out, or we're just riding a soggy bag of potatoes. If we measure what's going on with the suspension or with the axle directly for that matter, what we start to see in the data, if we perform an FFT, which is a fast Fourier transform, process the data to give us what's called a power spectral density graph. That will shows what power density exists at any given frequency. And that basically means how much of the time or how much of the energy that is in the system is occurring or being created at certain frequencies or responded to at certain frequencies. If we graph this, so this is our frequency, so there's a frequency domain, not time, not displacement, not anything else. We see these two poles, which will coincide with some variation of the natural frequency, which is obviously a damped natural frequency in practice, of the sprung mass and of the unsprung mass. What this basically means is that we have two separate vibration modes. One is the rider and the front triangle bouncing up and down quite slowly. And the other one, if you would imagine that if we flip the bike upside down and whack the wheels from the top down, right, so the rider's lying on his back on the ground and holding the bike above him, and we push the wheels down from there, assuming the rider is relatively rigid, the wheels themselves will vibrate, right? The hub and the suspension will oscillate up and down. Friction and whatnot will obviously put an end to that pretty quickly, but the frequency of that vibration is a second resonance mode. So we have two. We have one is the rider bouncing up and down, and the other is basically the resonance of the wheel. There are two main resonance modes. Using the terms primary and secondary can be very misleading here from a mathematical versus a pragmatic point of view, because there are many other resonance modes, right? For example, with forks, and if any of you guys have seen the pink bike huck to flat tests, you've no doubt noticed this, the forks themselves will vibrate back and forth at 90 degrees to the axis of their motion, which is in itself another resonance mode. If you're not familiar with the terms critically damped, underdamped, and overdamped, this might all seem like very airy-fairy to you. This is explained in one of our previous videos. The link will be below. You can also look up a lot of this on Wikipedia. Their page on damping has a lot of the basic concepts in there. Okay, so let's have a quick look at some of the maths behind this. This is a 2 degree of freedom system. So this K tire value is really only valid while the wheel is in firm contact with the ground. If it isn't, which it commonly isn't on mountain bikes, then that value is not necessarily relevant. The value of like the spring constant of the tire also varies immensely according to exactly the profile of intrusion that we have into the tire. So if you push the tire against the square edge, it's much softer than if you press it against something flat, where it has a much bigger surface area to generate force with. What we're mostly going to look at is the relationship between the unsprung mass, the sprung mass, the spring, and the damper in between them. I'm going to leave this out of it for the moment because the primary way that this interacts is that it adds to the spring rate here in order to determine the total stiffness of the spring that is trying to move this. Once again, if the tire is not in contact with the ground, this basically evaporates and stops having any real influence. So let's have a look at a one-wheel model. We'll have a look at the rear wheel of a mountain bike. Sprung mass, if we have a total sprung mass of a bike and rider of about 100 kilograms, then the sprung mass being borne by the rear wheel is somewhere around 65 kilos. The unsprung mass, again, that's the rear wheel, cassette, derailleur, swing arm, and so forth. The inertial components of that, let's say 3 kilograms. These are all absolute ballpark figures. They're not necessarily accurate in any way, shape, or form. Spring rate. If we calculate what a 450 pound-inch spring is at the wheel, if we've got a 160 mil travel bike with a 65 mil shock, 450 pound spring at the wheel, converted to metric, that is just over 13,000 newtons per meter. That's per meter, not per millimeter. So that's our spring rate as measured at the wheel. right? So not the spring rate at the shock. Our natural frequency of the sprung mass, so Fn sprung here, is basically the natural frequency that this part would tend to resonate at given the spring rate here, if there is no damping, right? So it's undamped. That would come out to 2.3 hertz, give or take. The natural frequency of the unsprung mass, however, is 10.6 hertz because we're using essentially the same spring rate, right? So again, this is undamped. We're not factoring in what the damper itself is doing just here. But you can see that this is significantly higher than this. Like, in fact, 4.65 times higher than that. If we calculate the critical damping coefficient, right, this is denoted by Cc. For the sprung mass, we get something like 1850 newton seconds a meter. This is a very confusing unit, I realize. What it actually is newtons per meter per second, right? So at 1 meter a second, how many newtons you're getting. Likewise, if we calculate the critical damping coefficient for the unsprung mass, we get 398 newton seconds a meter. So this ratio is the same. It's basically a ratio of these or these. It's the same number. What that tells us is that the amount of damping required to critically damp the sprung mass, albeit say 50% of critical damping, so a damping ratio of 0.5, is 4.5 times higher than what's required for the unsprung mass. So this gives us an obvious problem. If we were to aim to critically damp the unsprung mass, then we end up with something that is 1 divided by this number, so roughly 22% or thereabouts of the critical damping for the sprung mass. So either our sprung mass is massively underdamped, or our unsprung mass, that's the wheel, is massively overdamped. So this is basically trying to work out what is an appropriate damping coefficient at the damper. The compromise is that we typically end up with something that is significantly underdamped for the sprung mass and considerably overdamped for the unsprung mass in rebound, not necessarily in compression. The reason for this is pretty simple. If the unsprung mass is overdamped, so the wheel, it's not typically dangerous. It can lead to harshness, it can lead to problems with the wheel tracking the ground, but it isn't actually dangerous. However, having a massively underdamped, particularly in rebound, sprung mass can be dangerous on long travel bikes. It's less dangerous on short travel bikes because they just don't have as much displacement to use to throw you around. They can't store as much energy. This number, or this ratio here really, is a good indicator of why it is that we can't easily use standard vibration theory to tune mountain bikes. This is only one part of the bigger picture really, because the rider themselves is a huge influence on the bike. If it were not for the ability of the rider to actually damp itself basically, mountain bikes would be fairly much unrideable and we would need a lot more suspension than we have. That would mean basically bringing the natural frequency of the sprung mass right down. And this is why motorbikes, for example, like off-road motorbikes, would typically have around about 300 mil of travel versus typically half to 2/3 that for long travel mountain bikes. Besides the fact that motorbikes don't complain about pedal bob or anything like that, the reason that they need so much suspension is because the rider can't actually damp out anywhere near as much of the movement of the sprung mass as you can on a mountain bike. So that's one thing that works in our favor on a mountain bike. But for the time being, until someone comes up with some pretty clever tech to get around this, we are stuck with a significant compromise between our ability to fully stabilize the bike and to make sure that the wheel is really tracking the ground as well as it can. Properly damping out hub resonance, so wheel resonance, is quite difficult to do. Even though the damper itself is often overdamped for the hub mode, so the resonant frequency of the unsprung mass, it is difficult to accurately control that and minimize those vibrations. And they are a significant part of the total vibrations that the rider feels. Partly because they're never completely in plane or along the axis of motion of the suspension. That means, like I was talking about before, with the fork itself vibrating back and forth, a certain amount of that can't be just damped out, but it can be introduced by improper damping via the fork or the shock damper itself. So, yet again, this is another 20-minute ramble with not a lot of information that you can necessarily use, but maybe it will help shed some light on what the real compromises in suspension tuning are, why we come up against certain limits within current technology. There are always ways that this can improve, and a very coarse one is electronic suspension. When I say coarse, what we talked about recently with live valve and flight attendant, to some degree, they're actually trying to allow this, right? So they're providing a heavily damped mode for sprung mass when you are pedaling, and a lightly damped mode that is more suited to the free motion of the unsprung mass when you are not pedaling. The basic implied theory there is that we can stabilize the sprung mass in certain circumstances and allow for adequate motion, free motion of the unsprung mass in certain circumstances. I think as this concept gets developed over time, not specifically electronically, but as this understanding of the separation of the two there becomes better understood over time, we'll start to see some pretty interesting things. Anyway, that's it for this week. Feel free to shout into the void in the comments and get some discussion going. Anyway, till next time, see you then.